Okay, so we can start.
Yeah, I just wanna feel like welcome.
Okay.
Is on? Yes, on. Okay, cool. Hello everyone, and welcome to the June C++ Prague Meetup. So, yeah. Okay, thank you for coming. Of course, this time Jan is going to be talking about the zlib. This meetup is hosted by PureStorage, as I guess you have noticed. So for the next time, we actually most probably are going to have a different. Which camera? Yeah, it's okay. This part is going to be cut out from the recording anyway. Cool. Anyway, for those of you that haven't been on the last meetup, I'm Miloš. I'm organizing this. I just want to give a couple of service announcements, whatever. First things first, I need someone to replace me. Not right away. I'm actually from Serbia, and shame on you for waiting for me to come all the way from Balkan here to organize this. But the point is, I'm actually most probably going to go back to Serbia, and I would like this thing to keep going when I'm gone. So yeah, still I will be on Discord, and a lot of stuff can be done online. But the second point is that I'm just one guy, and I can get sick, and I want to go on vacation and stuff like that. So it'd be best if I didn't do everything by myself. Second thing is, if you work at a company that might be interested in hosting this, yeah, for now it's PureStorage, and I forgot the name of the company. Sentinel. Sentinel One. Okay. And now that I said the name, they have to host the next one. So yes. And other than that, if you want to give a talk, yeah, just let me know. I hope you are all on Discord, and if you're not, then you can probably find me on LinkedIn or whatever, or I don't know, get in touch somehow. This is intended to be very casual, so don't worry too much about it. It doesn't need to be production ready, because let's be honest, production isn't production ready. It's yeah, that was actually one of my funniest things when they say on conferences, like, this code is not production ready, and then you're like, have you seen our production code? Yeah. And other than that, if you really don't want to do anything and just want to come and enjoy, then yeah, you're welcome. And with that, I'm done, and Jan can start with the talk.
Right. All right. Okay, now I can hear myself. Fine. So this talk, don't expect any specific expertise from this. This is more of a. Wait, what?
Sorry, I would just, if you can promote Vesna to the panelist. Open Zoom. Open Zoom.
I cannot open Zoom because it's. Okay. I wouldn't. Yeah. Okay.
Okay, this one. So can you just, maybe you can because okay, it's fine. Turn on the front camera and then go online.
My own front camera. Okay. Okay. Fine. So now I'm also visible online. I don't know what's the purpose of this, but whatever. I think everybody will be looking at the slides anyway. Okay. So this talk is just about a little project of mine where I was trying to optimize some code, and just pretty much just a story how I found some little tricks and basically low-level tricks that might be useful for everybody. Of course, there is a GitHub project behind this, so if you will find this useful, you can use it. Okay, so for start, well, what I did was basically that I created a library for decompressing gz format, which is very known. The reason why I chose gz is that it's something that's used very often. And I thought that the open source library that's used pretty much everywhere for it is very user unfriendly, because so well, you see a library and I open the project and I have absolutely no idea how to use this project, how to compile it, which function should I call to use it, and so on. So I decided that I should just write my own library and try to make it also faster, if this will be possible. To start, I'll describe how does the gzip compression work. It uses the deflate format, which is also used in the zip archive, but there are some format differences elsewhere. The algorithm is the same. This algorithm is a combination of two types of compression. First is LZ77, which replaces repeating substrings with references to earlier occurrences. This means that the result is that there are 256 plain code words. Their meaning is obvious. Then there is one word for the end of block and 29 words for indicating that there is a repetition, and we can just refer to this and copy instead of including the whole thing. Afterwards, there is the Huffman coding. It, well, first deals with the problem that we have 286 codes, while, well, usually we have 256 possible values of a byte. And while at it tries to find the sequences that are as short as possible, so that we use less bits if some bits are more common. Here is a description, a little description how a Huffman tree can work for those who are not familiar with this. Although this is quite a basic example of coding well, coding as making a code, not as programming. That is so that's cool. So it's relatively basic, so I'm not going to go into much depth here. I couldn't make a better picture because I forgot to do it at home, and I was trying to do it at work, but GIMP works absolutely terribly on Mac, so couldn't figure out anything better. So let's say that we have some string, we don't know the length ahead, and we know that letter A appears 25 times, letter B appears 12 times, and letter C appears 5 times. We, of course, need yet another word to indicate that something is the end of this sequence. If you want to figure out the shortest way to write this on the bit level, a Huffman tree is pretty much the best option. Well, there are multiple ways to construct it, but this one I'm describing here is canonical. This, well, pretty much, well, the different Huffman codes have pretty much the same, well, we can have one that's more efficient, one that's less efficient, but we can always find one that is canonical, which is equivalent. So let's just not bother with further discussion. Why does it have to be canonical or not? So first, let's say that A will be encoded as 0. Then if something starts with 1, it means that there will be more bits and that it's something else than A. So we read the next bit. If it is 0, then it means that it's B. If it is 1, then it means that it's yet something else. Can you see my mouse pointer actually? Yeah? Okay, that's good. So so if there is yet another 1 after this one, so then we read the next bit and determine if it is a C or the end. This way, if well, the most common letter is the shortest, and well, the less common, the longer it is. There is an algorithmic way to construct this, but I'm not sure if there's actually some good efficient algorithm that makes the perfect solution for this, but it's not even important at this point. We are just decompressing. So yeah, what we can do in the gz compression is that one option is that there is just some static code that we don't need to define at the start. That one is used only if it is something really short that it's not more useful to use something custom. And otherwise, well, if we are using a custom, it has to be defined at the start of the block. So as I implied, the deflat algorithm is separated separates the compressed code into blocks, and the individual blocks use different Huffman trees. So if we are trying to parse this, the steps are relatively obvious. First, we read a sequence of bits and determine which code word it is. Because of the way how that we basically don't know the length of the word in advance, we need to write the whole, basically anything that's Huffman encoded in a reverse order of bits, which makes this a little more complicated and definitely much harder to read just by looking at the bits. After we have, well, found which word is there, we have to like check if it is greater than 256. If it is less than 256, we obviously just add the character to the output. If it is precisely 256, it means that we are going to read the next block. And if it is more than 256, it means that we are going to look at some number of bytes behind to copy a sequence from there. This has an implication that because the maximum length is 32,768 bytes, we need to always keep a buffer with this number of older bytes. And finally, we need to compute the CRC32 checksum and compare that if we did parse the right thing. So, well, this is an algorithm from the 80s, so it's not something extremely complicated. So the first step was reading the sequence of bits. Well, the obvious solution is that we can just, well, find the bytes from which we want to read the bits in the span that we are reading, and just remove the unwanted bits using bit operations. And finally, when we take these sequences of bits from these bytes, we just concatenate them together. Another part is bit reversal. If you want to reverse the order of bits in a byte, there is nothing that, well, doing this in a loop is obvious, but if you look at like what's the trick to do this faster, because a loop, like going through 8 iterations just to do one byte, it looks like pretty inefficient. So, well, I thought that this should be something that's a pretty common thing. So I looked at Stack Overflow and found this answer. This basically uses integer multiplication to shuffle those bits accordingly, because if you use an 8-byte long integer, we have pretty much enough bytes there to displace any bit wherever we want. This seemed like a, well, good option. So I went on. Next part was to identify the Huffman word. Well, at university, they would have explained that, well, you have this Huffman tree, you read one bit, check if it is 1 or 0, and then proceed as tree traversal. However, I have one problem with tree algorithms, and that is that I always make a mistake. I rarely manage to do a tree algorithm without making a mistake. It's horrible to debug because there are all those pointers and one doesn't know the depth exactly where he is. And like, let's stop it in the debugger and suddenly we see we are here, but in which depth are we, and so on. And another thing is that, well, we know that bits are, well, trees are generally rather slow because you have a lot of indirect jumps and usually ends up with a lot of dynamic allocation, which means that places are far away from each other in memory, and also the allocator isn't exactly the fastest thing. So I thought, like, okay, I should do something else than a tree algorithm. I didn't even start with it. So I got this idea that, well, most words would be 8 bits or shorter. This is just pretty much the requirement because we don't have so many more words than 256. So most of the common ones should just fit there. So I thought, like, okay, I can make a table with 256 values of the first byte. And well, actually I have a picture of that. Yeah, here. That, well, a table of 256 values, that's not much. So if I have a word of length 5, for example, if those are just zeros, so the first 5 zeros and all the possible bits that can follow should be should just all be the indexes that point to the value that, yeah, to the length and the actual word I have parsed out of that. So pretty much, well, here's a visualization. Well, I'm not sure if this is clear. Nobody's commented yet anything. Yeah, I guess everybody understand. But, well, just make sure that every word, yep.
Yeah. Is it the length of the prefix of the word, or is it the length of, like, count of the items in there?
No, the length of the actual word is there. Of course, if it is more than 8, then this means that we need all these 8 bits and yet something additional. So this had to be handled specially. However, to handle the situation, I well, saw that this is not going to be a common situation, and there won't be more than 286 words. So I just created a static table with 286 elements and just put all the stuff there. And in case it didn't fit into this table, it was just linearly searched. Sounded like a good option. So next step was that I was reading some extra bits of copy lengths and distances. There is a table of that, telling that usually these are the words after 256 that tell that we should copy some number of bits. We cannot copy less than 2 bits because just encoding the copying operation would be longer than actually just writing it out. Up to 10, it works just obviously one word, one length. Then for 265, this means that it has to read an extra bit, and according to it, it reads either 11 or 12 bytes. sorry, it copies 11 or 12 bytes and so on. It just continues that more and more bits. And this can go longer and longer lengths of copied content. I was thinking that, well, this table actually would be relatively large. So how about just figuring out an explicit formula? So I figured out an explicit formula for this. No multiplication, just some bit operations. Seemed pretty fast. The next step was that if I was copying something from a few bytes from behind, it was clear that I can just, just do a mem move. It, well, did work. However, there was the problem that sometimes it could encode that, let's say, copy 10 bytes from 3 bytes behind. This means that the sequence was repeating because it was just overlapping with itself. So I had to add a little loop to handle this to the mem move. But, well, it wasn't complicated. For CRC32, well, the definition is bit by bit, which is obviously very slow. This is a pretty common problem, so I just looked up some solution that pre-computed the table. The code that I found was actually, well, I found it needlessly complicated. It was using a stat transform, and it still needed the index, so we put the index into the closure of the lambda called by this stat transform, which I found really complicated. I replaced it with a simple for cycle. The length of the code actually got halved. I have nothing against monads, but sometimes it just makes the code more complicated than necessary. So yeah, I did a CRC32. Oh yeah, I need actually to use this table. So pretty much anytime I was adding some bytes into the output sequence, I ran it through this loop. And then I I spent a lot of time debugging, and finally I benchmarked it against gzip, measuring specifically the user CPU time. And I found that it decompressed the data at 50% of the gzip speed. Well, obviously not all of my assumptions were correct. I obviously, well, didn't do everything in the optimal way. So it was time to use a profiler. The easiest one to use is, of course, call grind, because you basically just open the program in it, run it, and then open the output in kcache grind, which is a GUI application that tells you some reasonable assumption how long will all of this take. And well, the data is very exact. However, of course, this is still some sort of simulation, so it's not, although it's accurate, it's kind of a model, but I'd say that, well, it helps a lot. So I was looking at the bottlenecks. The obvious problem was the bit reversal. I found that it was like a really significant portion of the time. The obvious problem was probably the, well, it looked like the multiplication is the most expensive instruction. Although this is still not a floating point operation, but still a long integer takes quite some time to multiply. So to handle this, I have decided that, well, why not just use a table? And, well, the time this operation took became, well, almost neglectful. So actually using a context per pre-computed table is often a fairly efficient solution to problems. Well, another very visible bottleneck there was the operation of extracting a bit sequence. The problem was that there was, well, a lot of operations that were done to actually extract the bits from each of the bytes that was affected by this sequence that I needed. Well, I was thinking about it, like, how could I do this more efficiently? And I found that the best option is to use an unsigned 64-bit integer as the buffer. And in that case, I could just take the last 8 bits, get it out of it just by bit shifting. And then I identify which word it is. And then I just bit shift the rest. And always it starts at the right location where I want it. So here is a drawing how this roughly looks. First, I read the last word, look it up at the table, find which word it is. And then I found that it was a 5-bit word, so I remove 5 bits by bit shifting it down. Then I again look it up at the table, find the length, use this word that was behind it, and again just bit shift it by this length. And so I continue until I have less than 16 bits, because the longest words that's permitted by the specification is 16 bits. So that means that, well, I cannot do much. I need to refill the buffer. And so, well, refilling the buffer isn't something that done so often. So yeah, I did some bit casting to convert it again into an integer and add it into this value. If you look at this closely, there may be a little issue that I have actually switched the order of bits here to the, so that it's closer to the realistic situation. Because, well, we need the last, oh yeah, the first bits are the ones that can vary, because we don't know what word follows, and it's actually the other direction, but the specification probably had this operation in mind when it was designed. So pretty much it's just happens to be ordered the way that this can be done. When I tried this, I found that the bottlenecks were gone. The decompression speed was about 90% of zlib. But at this point, there were no obvious bottlenecks, but it still was slower. So I had to look at something that was less obvious, and I had to get more speculative. So I have kind of looked at the place where the lengths of the extra, well, the additional lengths of the sequences that we are going to copy, that maybe this explicit formula was too complicated. So I decided to replace it with a table. I used the table, but unfortunately, well, Kcachegrind reported that less time was spent on it, but I observed nothing in the comparison. So, okay, this probably did something, but nothing observable, wasn't worth the effort. Another thing that I was looking at was that at this point, the CRC32 checksum was taking 25% of the overall time, which was quite a lot for something as simple as a checksum. So I was thinking, like, what could I do with this? And well, I couldn't think of pretty much anything, because the problem was that every time there is one operation done, it takes the result of the previous operation and it uses it at the index. So this is something that's called data hazard, when you have a long sequence of operations when each depends on the result of the previous one. So I was thinking like what to do with this. And then I thought, well, somebody has definitely had to look into this and try to figure out something better. Somebody who's definitely more knowledgeable on algorithms than me. So I put it on Google, fast CRC32 checksum, and I looked at the first result and it was it. I found that some engineers at Intel were looking at this, and they have actually figured out a solution that can do this by 16 bits, which was using, I'm not sure if this was 16 or 32 tables. I have found the code for that. It was absolutely unreadable, full of C macros. It even contained some code that told how to generate these tables that were explicitly pasted into the source code. So I thought like, hey, I don't want to work with this because I wanted to make it header only, and like putting these 1,000 lines of copy pasted numbers into it, that wasn't something I wanted. So I figured out the context, a way how to do it using context per functions. This all broke down to like 15 lines of code maybe. That was run on compile time. I didn't even see a difference in the in the time of compilation when I added this, and it was all just pre-computed. So okay, just got rid of this huge table. And the problem was that it generated a table that had 16 values, and it needed to compute XOR out of it. So of course, there was just a huge line of 16 numbers, each of them XORed with the other. I was thinking like, isn't this a data hazard actually still? Because, well, if we are just XORing it one after another, the order of this operation is predefined by the compiler, but, well, no, by the language standard. But it would be the fastest if we use some kind of divide and conquer approach, just always XOR 2, then XOR 4, XOR them by 8, and then we get the result. I couldn't force the compiler to do this. I was thinking like, how the hell, it's just always linearizing the 16 XORs, and it could be visible in the performance. And actually the only way I could force this was to write these XORing functions. Well, no, the actual computation of each of these 16 numbers into a recursive function. And then I was just doing a recursion, and all of this had to be of course, in compile time. So I just basically had to, well, the code became fairly complicated just to put this, just to enforce the recursion here. But at this point, I saw that, yeah, it actually does 2 and 2 and 2, and then 4 and 4 and 4. So no, the results of these two pairs always, and yes, finally did it in the right order. And yeah, the difference was visible. So this seemed pretty good. Next problem with performance I saw there was that it looked like the linear search with the longer words than 8 bytes actually was a problem. Previously I had found that using a hash table is, well, slower than a vector, even if I have to do linear searches with a vector with lengths even over 200. And I was thinking like, this should be even really fast, because you just make one operation. This should be like absolutely perfect for speculative parallelism done by modern CPUs, but obviously this wasn't so much the case. So, well, I couldn't use really some hashing because this would be relatively slow and there would be overhead and so on. So at some point I realized that, well, why don't I just source the table properly? That instead of, if the word is longer than 8 bytes, then I just write the index into the table and it just searches only the words that start with the same prefix that I have already parsed out of that. So, so basically there would be only a very few options that start with this one word. And yeah, it worked. At the end, I got the 110% performance of gzip. So, oops. Yeah. I forgot that at one point, yeah. I wasn't reading the slide and then I did a mistake. This is the slide about the algorithm that I found from Google, no, Intel. Previously, I found that the problem was that CRC32 was called after every byte. And well, no, was called at the end of every submit, which was a problem because I just wanted to write it into a file. And only at that point, I just did a CRC32, which was, well, just a lot of CRC32 on every byte that was there, which wasn't the best. So I decided that it would be better just, and whenever I'm adding a single byte, I do a CRC32, which means that the previous CRC32 value was computed long before this, or not long, but longer before, not just a lot of CRC32 loops in a sequence. And this did some improvement, but it wasn't as good as the, well, 16-byte CRC32 that I found later. Yeah. Here is even the code hours, the context per code for creating the tables. Yeah. And after doing all of these, I got to 120% of zlib's decompression speed. At this point, I was satisfied with the result. I shared it on Reddit. And somebody told me that, hey, this is good, but you didn't think about one trick that the zlib is actually doing, and that is that the Huffman, well, when the bits are looked up in the table, they are not reversed before looking into this table because the table is already reversed. So that I avoid the bit reversing operation except for the time when I'm writing the table. So this looked pretty good and I got to 130%. And yeah, that was pretty much all. It was clear that there is, well, one bottleneck that I cannot really get rid of. And it is the fact that in order to read the next word of the sequence, I need to know the length of the previous word, which means that there is a data hazard, but it's a part of the algorithm. I cannot deal with this in any way. So at this point, I was thinking that, okay, I guess this is the limitation. And I suppose this is the reason why formats like LZ4 and ZSTUT, how does it read it? Oh, this ZST format, they are generally much faster for decompression. I suppose that is because they avoid this data hazard, and this allows using vector instructions much better. Yeah, I was thinking about some further options like that, for example, I might just make some buffers larger, or maybe some other things, maybe compile this profile-driven optimization or something. But at this point, I wanted to make it easy to use, and making just some other tricks could just make it this more complicated. And well, I didn't want to go too much into that, but that's where I stopped and started focusing on creating something for compression. And so far, well, I cannot tell that I was very successful. So far, I have worse compression rates, and it's also slower. So I'll have to think about it, what I'll figure out. And yes, there might be a sequel once I get the compression part working. So far, I haven't made anything. It's all on GitHub. If you want to have some easy to use gzip decompression, you can use it. I have just created it, written in a way that you can just use it through a stream interface. So you just create a class, you put the file's name into the constructor and then use it as a stream. So it's super easy to use, it's header only. And well, but I wasn't really trying to advertise this. My main point for this was that not everything in optimization works exactly as you think when looking at it for the first time. That's why I started by telling things that were actually wrong, as it turned out. And well, some parts don't really matter. For example, everybody tells that stream is slow, but I found that it spends minimal time there. Other people say that, yeah, C++ is slower than C. Well, not necessarily. So, well, I guess I'm open to questions now. Any questions? I suppose you have, because I definitely told a lot of things that were not correct.
This 130% speedup is consistent on different kind of data, like long words, short words, or it's just for some limited samples you just chose?
Well, there is a standard sample on which compression is tested. This sample is designed to contain all kinds of patterns of data that may need to be compressed. When I was looking at it, there was well, just a lot of text. I think all the books written by Charles Dickens. Then there were some bitmap pictures. Then there was some compiled installer of Firefox, and some pictures, some data that was already compressed and you couldn't do anything about it. And I don't remember all what was there, but this was published by some university and it is used as a standard benchmark for compression.
Yeah, but the results were consistent for all the data. It was 130, or it was like fluctuating.
Well, I wasn't testing it on individual parts. I was just testing it on the whole benchmark to compare it, because well, I could have looked into specific parts where it could be faster, where it could be slower, but I didn't think of that.
And it might be another place when you can optimize it. Depends on the kind of data. The second question, did you try it in Little Indian and Little Indian, different compilers, or like that, or just like one?
I think I tried different compiler, but it's in C++. But well, the problem is that C++, well, first is C++20 is not supported really well by Clang yet. I was doing this on GCC, and I just tried it compiles, but I think I didn't try Microsoft Visual Studio because, well, it's harder to get to. So I was just working on GCC, but zlib is compiled with GCC anyways. For benchmark, this is correct, but for a general purpose library, well, yeah, this is a problem. But on the other hand, I wasn't using anything compiler specific, so I guess it should work. But well, the compilers don't handle everything perfectly, so there might be some problem that I didn't look into.
Yeah, big Indians or Little Indians, both kind of compilations, or like Little Indian, like?
I have, well, C++20 adds an option to check for the NDN at compile time, but I'm not sure if I did test big NDN.
There's a lot of bit operations, just curious.
Yeah, I wrote it, but I'm not sure if I tested it at this point, or maybe I tested it at some early point and I didn't test the version that's currently there. No questions, really? Sure, I must have told something so inaccurately that you must have seen that it was wrong. Come on. Did I explain everything correctly or what? Or everything in a way that was clear? It couldn't be clear. This is weird. Yeah. Okay, yeah, I can show you the code. It's on GitHub after all. Yeah, yeah, I'm prepared to argue. Yeah. No, or maybe I did, but I didn't know it was big endian because in those times I didn't know what is big endian, little endian. I was thinking that somebody speaking about some Native Americans.
Me neither, for the record.
Mac PowerPC, it was big endian. It's outdated. Yes.
I'm sure that existed.
There are, I guess ARM processor can be switched to big endians.
ARM processors can be
Yeah.
Okay, so this is the
Got it.
So yeah, this is the code base. No, the GitHub repo. Here is an example of basic usage. You just create a stream and just use standard functions like getLine. This is of course slower than if you want to use a stream efficiently, you have to use different functions. I have provided some functions that should not suffer from the inefficiencies of parsing through stream. Here are some examples. The compression part isn't here because I wasn't very confident to publish that. Okay, so this is the source code. Yeah, I was writing in C++20, so I used templates to make it possible to do some configurations. I've used concepts to like validate if these templates are used as arguments, if they are correct or not. Yeah, here are just some settings. Yeah, and this was the basic CRC32. It's just copied. Not copied, I have edited, I have written this, but I was looking at some different code that was, in my opinion, unreadable. Yeah, this is the CRC32 that was supposed to be efficient. Here is the lookup table. I could have figured out some trick how to avoid writing down all the 15 elements in a sequence, but when I was thinking about it, making this at compile time would probably make it even longer than writing out 16 values. So, well, I guess this is better this way. Yeah. Yeah, and this is just the loop that goes through all the parts of 16 bits, and this is the final part, 16 bytes, the final part that goes byte by byte when we are at the end of the section. And yeah, here is a context for flipping the byte order in case it is a big endian. I think I didn't test this part because, well, it's a little bit difficult getting access to big endian. Well, okay, the next, here I figure out a trick or array filler for building compile time arrays, so that I wrote a lambda that took an argument as, that took the index as argument and produced the value. So this allowed me creating compile time tables without too much code. So basically, if I wanted to generate the reverse bytes, I use this old formula. And yeah, what I did open here. Just use the, so I just use this formula, but I didn't compile time using this array filler trick. Yeah, byte input, this is just the buffer. It allows reading the values by bytes or by larger groups of bytes. Bit reader, this was doing the all the shifting by bits, so that I could read by sequences of bits instead of by bytes. Yeah, here is a table of values for removing some number of upper bits. I'm not sure if this is actually faster than using just 10xFFFF and bit shifting it always before the operation, but I just wrote it this way. Not sure what was my logic here, but I don't think this was a bottleneck, so it didn't matter so much. Yeah, I had a distractor that was doing some flushing, I think. Why am I running out of battery when I'm connected? Okay. Oh, damn it. What's going on? I started sharing. I didn't know what is shown. Damn it. Okay. Yeah, it's also not charging. Okay, this is useless. Okay. It said there is a charger here. There's no charger here. Okay, so I'll have to end before I run out of battery. Yeah, this is the byte output. This was basically just an output buffer. It was supposed to keep a certain number of bytes there so that I could copy them if there was a repetition of the sequence. Yeah, encoded table. This class was handling the Huffman trees. This was the Huffman tree generation. It wasn't actually trying to compute a good one. It was just parsing one from the input. Yeah, this deflate reader, this was just keeping the possible encodings, keeping the state of it. I was trying to avoid dynamic allocation in the whole thing, because dynamic allocation is not exactly the fastest thing. So I used that variant to keep all the possible states here. Also, the buffers could be just weren't too large, so they could be just placed on stack, and they were dependency injected. So if somebody had some special requirements, he could just construct the final class differently. And these are the basic utility functions. Read deflate into vector. You just put the reading functions as an argument. You get a vector. Alternatively, it could just read a stat span, parse it into a vector. Yes, but this was just for the deflate algorithm. This part, deflate archive, is also for yeah, was it for the header? No, it wasn't for the header. This was yeah, this is just for reading it, but without just doing it all at the same time. I've put some functions like read sum, that was just reading in some sequences in the way how it just came out of the file, read by lines, and so on, just some basic utilities. If somebody doesn't like stat stream. Yeah, gz file info, because the gz archive has some header, so this contained the parsed data out of it. What I didn't do is that I did some dynamic allocation here because, well, this was just some utility around it. This wasn't the main algorithm. You just to open the file, which already needed the file system, so unusable and embedded anyway. So, and yeah, this was just extending the gzip archive by adding the yeah, this was just extending the archive by adding the start necessary to open as a file, not just as a buffer. And finally, implementation using streams, which made I ended up creating 4 constructors for different ways of reading this, but the most obvious one was, of course, putting just the file there. And also there was a possible argument for the number of bytes that are kept there for the case somebody wants to read, wants to do this unget operation that StudStream has, so that they know how many bytes can they look back. Most of the logic is in this gzip buffer. This is basically just implementing your own StudStream is fairly easy if you know what to do. There is it can be found if you look at it if you look it up, and well, pretty much just getting your own input source running with StudStream is fairly easy. And I found that if you aren't using its functionality to parse it, it's pretty fast, and it's a pretty standardized way of accessing stuff. So everybody will know how to use your code. I guess this is all. Maybe some example is the decompress file. It's using also some timing and metrics, but actually, when you are making the stream is just basically use decompress, and then there is this operation to read it into another stream, and closing is just really easy to use. Okay, any remarks on my code style?
Just a suggestion, could you put link to the GitHub to the slides and question if the slides will be shared afterwards?
I can share it afterwards. If my laptop won't run out of battery right now, how much is there? 6%. This is bad. I have to stop sharing right now. Okay. I'm not sure how to communicate with you right now. I could put into slides, but I don't know how would I send it to you.
Yeah, I don't know if everyone is on Discord, but you can just share it on Discord. And
yeah,
also,
I can share it on Discord. But
also, this is going to be recorded, and I will most probably make a YouTube channel for this meetup. So I think everything will be shared there.
Okay, I've stopped showing my face here because I would run out of battery. Zoom is very battery hungry. Okay, yeah, I can share. I will send it to you. Should be fine. Yeah. Oh, yeah. Yeah. There is just one little problem with that I don't have this Discord on this laptop, but should be good. Yep. Okay, I'm pretty sure that if you look at it into itself, you'll find some place for improvement, or some flame variable like code style, like using signed integers everywhere, except for bit operations. That one is obvious. That must be unsigned.